Okay, good evening, students. We are going to start a new topic from the coordination compounds, isomerism in coordination compounds. This is a very important
Yes,
topic. Here we are expecting good number of questions from isomerism. We already know when I say isomerism means you will see that their formula has to be the same students. So they have the same chemical formula, but there could be different arrangement of atoms, students, and because of the different arrangement of atoms their properties will also be different. When I say isomer means they are different compounds, and if they are different, naturally, how I will say different, one criterion is that they have different physical and chemical properties, students. Melting points could be different, you will see colors are different, or sometimes the
okay,
reactions may also be different. There are two types of isomerisms which we will be discussing in the coordination compounds. These are stereoisomerism and structural isomers. In stereoisomers, you know the position of atoms in space is different, but the bonds are the same. Whereas in structural isomers, the bonds will be different, students. The atoms which they are linking their bonds, there will be differences in that. So let us see
okay.
what type of isomers are there and questions, the type of questions which can be asked students. First of all, students, I have on the screen ionization isomers. What do you mean by ionization? The word ionization means what, student? Ionization. That means when you will put your coordination compound, supposing you put in water, students,
It will dissociate.
then what will happen? It will produce different ions. The ions are produced which are different, students. Different ions are produced. You already know in the coordination sphere, coordination compounds, the the ligands which are joined in the coordination sphere, they are not ionized, students. So which ions are ionized? Only which are outside the coordination.
Outside the sphere, coordination sphere.
So the ions which are counter ions, which we call as counter ions, they are the ones which are ionized, student. So counter ion in a complex salt, why it will happen? That is a question. For example, student, I have on the screen, I am writing CONH3. When we do examples and questions, then we learn more. That is our experience. When we do questions and examples, it helps us. The definition is only a definition, but it becomes more clear. Here I have a compound, student. This is my coordination compound. I have another coordination compound, student. What has happened? What has happened? This is Cl. This is inside the coordination sphere.
Yes, sir.
Now there is another ligand which has a potential to become a ligand, but it is a counter ion here. So what
B
can happen,
ion.
student? What can happen, student? I can write another coordination compound, student. These two are not the same coordination compounds, but molecular formula is the same. Tell me, they have the
Yes,
same
sir.
chemical formula,
Yes, sir.
but what is the difference, students? As you can see, can you give a IUPAC name of the two compounds? What is the IUPAC name of this?
Sir, the first one will be, it will be,
This gives us a good revision, students. We are confident of what we are doing, students.
chlorido,
So,
cobalt,
what I am saying, the
BX plus 0 minus
counter
1.
ion itself
The
can
first one.
become a ligand. It can become a ligand. Student
Var,
can displace,
Urali.
can displace
99.
student the ligand. Ligand.
Yes, sir. Sir, here it will be. First one will be pentamine, chlorido, cobalt, 2 bromide.
Okay, this is plus one. This is okay. Okay, that is okay. That means okay. We have learned a lot of things which we are not forgetting. Learning and repeating revision always helps us. This is also our experienced student. Okay, that was the correct answer given by you. Now the question, what I am trying to say, student, these are the examples. If this gets ionized, student, what are the ions which will it produce? If the first one on ionization and the second one ionize. If this ions ionizes, what are the ions you are getting?
The whole coordination sphere will be 1 and chloride ion will be 1, Cl
And
minus.
if this one is ionized, student, what we are getting?
Whole coordination sphere plus and bromine minus.
Okay. Now, now you understand what do you mean by ionization. Do we have to remember the definition? Once they asked what is ionization isomers, give examples. See that question can be as simple as that. Now the confusion is what definition I will write. Array, if I know it, I can make my own definition. So on ionization, student, the counter ions which are there are different. So here you have Cl minus ion, and if you have to perform a test, student, you add silver nitrate. This question was framed once. So what will happen then? What precipitate you are getting? AgCl, and
AgCl,
here what precipitate you will get, student? You have Br minus.
AgBr, AgBr.
So this here you will add silver nitrate, student, and you will get AgBr. And you know this is white colored precipitate, this is pale yellow, and this will dissolve in ammonium hydroxide. Therefore, students, ionization isomers are those isomers which on ionization are giving you different ions. And that will happen only if the counter ion can itself be a potent ligand. It can displace the ligand which is present inside it. So here we have shown the structure of this also. This complex is octahedral, student. This is octahedral. There are 6 ligands. How many ligands are there? 6 ligands. Is it homoleptic or heteroleptic?
6 ligands.
Is it homoleptic or heteroleptic complex? Or heteroleptic complex, students? Homoleptic or heteroleptic?
Heteroleptic.
Heteroleptic, okay. Everything, you know, every word which we have learned is being used. Heteroleptic, student. Hetero, am I right? The spelling I have given it wrong here. Heteroleptic. It is not homoleptic. The definition was asked what is heteroleptic complex. Heteroleptic complex. Because the ligands, you have two types of ligands, 6 ligand, 5. You have NH3 and other one in the first case you see
Cl,
Cl. In the second case NH3 and Br.
Br.
Now you can see that on ionization they are producing, and the important point is that this the ligand outside has the ability to displace the ligand which is present inside. That is important point. And see here we are trying to show you complete geometry of this also. This Cl is linked with the cobalt. Here Br is for the ligand. Here Cl is a ligand, student. So the difference is very clear in ionization isomers. In ionization isomer, there can be no further discussion on it. It is so clear. And we can distinguish by performing the chemical tests, whatever are possible, as they have been asking such questions in the paper. Next question before Ashish student. They said ki in the question they gave you these two compounds. They say what type of isomers are these? What type
Uh,
of isomers are these student? Question is like this.
so these are ionization isomers because
Ionization isomers.
this.
Example of that which I have given. What is the IUPAC name of the student?
So the first one is this is pentaamine sulfate cobalt bond 3 bromide. Sir, the name of the first one will be pentaamine sulfate cobalt 3 bromide.
Sulfate or sulfato?
Sulfato.
Okay.
Sulfato.
All right. So another question was given on this. The second question was how will you distinguish or identify the isomers which are there? You are given these two isomers. How will you distinguish these two isomers, students? What is the
This
difference between the two isomers?
84. Sir, we will add silver nitrate solution to both of them.
Silver nitrate to both of them. This, of course, you can be see there. What I will do? CH3N5 SO4 Br minus. If you add silver nitrate in this, you are getting AgBr. In the
Yes,
second
sir.
case, you have CONH35Br 2 plus SO4 2 minus SO4 2 minus. You will add barium chloride. What will you
Okay.
get? So you will get a white precipitate. So we can perform the chemical test also. Sometimes the questions are asked on that basis. Question can be changed in the paper. ठीक है? We are clear
Yes,
on
sir.
ionization. That on ionization, different ions are produced. And the counter ion can become a ligand. It can become a ligand. One, two, or more can be there. It's not necessary that it could be as simple as this. And there could be more than one here, which can be. Okay, no doubt
Okay, sir.
here.
No, sir.
All right. Now we are coming to the next one, student. What we are saying, the name will tell us solvate or hydrate isomers. When I say hydrate, solvate, of course I am talking of H2O. That means there is a difference in the H2O, student. What difference? One H2O is inside the coordination sphere and one H2O is outside the coordination sphere.
Okay.
What is the difference? See, what they obtained, what was found, student. Here I have given three compounds: Cr, Cl2, H2O4, Cl. This was bright green colored. This was found to be gray green colored, and this was found to be violet color. Do they have the same chemical formula?
Yes, sir.
Chemical formula is same. But what is the difference, students, in these compounds? What is the difference? What we have found?
Number of water molecules inside the coordination sphere and outside.
Okay. You can see what has happened. Those water molecules, student, which are inside are the ligands actually.
Yes, sir.
And those which are outside, they are not the ligands. They are not the ligands, but basically the solvent molecules, free as solvent molecules. What I am trying to say, student, for example, if I say CrCl2 H2O4, student, Cl2H2O. Here, student, these are the four water molecules are the ligands. They are bonded with the chromium, students. But when I say in this case 2H2O and Cl, this is a counter ion, and these are they are free. They are free in the solvent. Where they go, they are free, student, as solvent molecules. They are present as free solvent molecules. Free solvent molecules. So these are free solvent molecules. And in this case, you have seen what is happening, CrCl2 H2O4. So there is a different number of water molecules which are present in the ligand. Four water molecules are the ligands, five water molecules and six molecules are the ligands. And then you get different colored compounds. Since the color is different, that means they are different compounds, and experimentally they determine which how many water molecules are bonded or how many water molecules are acting as ligand, students. And here we have shown you the structure of these so that they become more clear.
Yes, sir.
So this you can see, this is a Cr, the six water molecules bonded with the chromium. Six water molecules. So this CrH2O was found to be violet in color.
Okay.
Violet in color, student. Violet. And this one, here what has happened? One Cl, you can see, has displaced the water molecule. The water molecule, how many water are there now? Five. And outside you have Cl2, student, and this is gray green colored. So such isomers are called hydrate isomers. They are called, student, hydrate isomers.
Okay.
So how many we have got? Three of such hydrate isomers, and there could be more than three, students. It is not always that there will be three hydrate isomers.
Okay.
We'll be able to write more than three also. In some cases, possibilities are there. Okay. So these are free water molecules in the solvent free as a solvent, and they are present as acting as ligands, forming coordinate covalent bond with the metal ion, students. Even the colors have been different. Now this has been asked many times. This is again important question, student, because they ask you repeatedly. I would say that the meaning of the words explains to us a lot of things.
Yes,
Linkage
sir.
isomers. Now, linkage means the linkage difference is there. The ligand should be such that it has more than one atom which can act as an electron donor. But at one time, only one of the two bonds or act as a ligand. And you already are aware we are talking a lot of these, you know what type of ligands it should be.
Ambident.
Ambident, this is the important word. I said this is important. Some question could be there on ambident ligand because it is repeatedly being asked in large number of exams. And we already know some of the examples: thiocyanito, nitrito, and in NO2, you know what happens. Nitrogen can act as a donor, or oxygen can act as a donor, nitrito. So students, for example, they say that CO NH3 5 NO2 Cl2 Cl2. Now here what it means, nitrogen is bonded to the cobalt,
Yes, sir.
and if I write CO, ठीक है, CO
Okay.
NH3 5 students, ONO student, then what happens? So if I change the sequence student in this case, what is the result of that? Here the nitrogen is linked with the cobalt, here oxygen is linked with the cobalt. What is the IUPAC name of this compound student?
Yes, sir.
What is the IUPAC name of this compound?
Uh, it will be pentaamine nitrito O cobalt minus two. Sir, the first one would be pentaamine nitrito O cobalt 2 chloride.
First one, this one nitrito. This one will be nitrito O now, not this. Colors were found to be different
The
students.
first one.
First one, okay. The colors were found to be different. One was red in color, other was yellow in color. These two, they are called linkage isomer student.
Okay.
So the condition of linkage isomer is very clear. It should be amide and nucleophile, and they can bond either of the atoms. So there will be two such isomers. If there are two atoms which can bond through either of the atoms, and for example, in this case, they found two isomers were obtained, two linkage isomers were obtained. One was red, other was yellow in color. So here again we are showing the nitrogen is linked, oxygen is linked. So this is an example of linkage isomers. This is very important. This is very important. This has been asked many times. Okay, we are going further, students. Now what do we say? Further, another one we are talking of coordination isomerism. Coordination isomerism, student. Here you can see that I have a complex compound, student. Both cation and anion both are complexes. This
Okay.
is a cation, this is an anion. So when you have a cation, student, cation, cobalt, NH3 6, this is 3 plus, cationic part, CrCN6 3 minus. This is the cationic part, and this is the anionic complex. So you have a cationic complex, you have a anionic complex, students. Then what can happen now? What can happen, student? See, this chromium is bonded with 6 CN ligands, and cobalt is bonded with 6 ammonia ligand, students.
Yes, sir.
Then there is, this can exchange. What can happen? This, there could be exchange there will be could be exchange of such metal ions. Chromium comes here, cobalt goes there. What it
Okay.
means? Cobalt becomes bonded with Cn and chromium becomes bonded with NH3 students. Then another complex will be formed, which will be different from this. And this will be example of coordination isomerism student. Coordination isomerism. So interchange of ligands between cationic and anionic entities. What is happening? Interchange of ligands between cationic cationic and anionic entities. ठीक है? There is an inter-exchange of the
Okay.
of different
Okay.
of different metal atoms or ions. Then this will give rise to coordination isomerism. Here you have seen the example very clearly. First case, cobalt is present and the ligands are NH3. Ligands are NH3. In the
Yes,
second
sir.
case, you see what has happened. These two are the chromium is bonded with six ammonia molecules and cobalt is bonded with six CN cyano ligands. So what has happened, students? Interchange of ligands has taken place and you are getting two isomers. These are called coordination isomers. They
Okay.
are called coordination isomers. They are again different compound, students. ठीक है?
Yes, sir.
We have tried to show it so it's more clear. We won't forget them. So if you have CONH3, he will say the question was like this. Write the, you can see the question can be put in many ways. Write the coordination isomer of isomer of CONH3 6 CR 3 and 6 2. And all you have to do is very simple. You exchange the metal which is there. What I will do, no problem, I will simply exchange that.
Chromium NH3
And cobalt.
L6.
So these two, if they are given, what type of isomers are they, we
Yes,
already know.
sir.
This is what we call as coordination isomers. Here we have another example, student. What has happened? See, if I exchange, students,
Copper and zinc are exchanged.
then what will happen? You then here, what is the name of this? This is a cationic part. This is the anionic complex. Cationic complex.
Anionic.
This is tetraamine zinc 2.
Amine.
This is tetrachloro or tetrachlorido
Tetraamine
cuprate because it is an anionic complex.
cuprate.
So then
2.
there will be exchange. The names will
Yes, sir.
also change, students. There is a change in name. What will be the IUPAC name of this compound?
Okay.
What will be the IUPAC name of this compound?
Sir, your voice is cracking.
Voice is cracking.
Yes, sir.
that then internet could be becoming weak from either side. But
Yes, sir.
the board is visible.
Yes, sir. Board is
Okay,
visible.
okay, no problem. You will get a recorded video also if anything goes.
Yes, sir.
We got the answer for this. This is a cation, this is an anion. So this is what hexamine, hexamine, cobalt
Uh, hex hexamine, cobalt.
three,
Okay.
and what is this? Hexacyanide,
Cobalt 3.
hexacyanide,
Nido.
chromate
Chromate.
3. So this is the important question sometimes
Chromate.
because one is cationic part, other is anionic part. They will test the students in many ways. Question can be put in many ways. There is no reason why any question cannot be put, as they ask all types of questions students, and we should learn to understand what type of isomers we are talking, and how to not only cram the things, not cram, but how to learn these, the basics of these isomers. The words will be speaking itself. That's what I'm trying to say. Each word has a meaning. Let us understand.
Okay.
Because NCRT, every line, has a meaning. Every word has a meaning. That is the question, student. When we write a word, then we have to understand that word. And if we don't, then we are passing time. And then students to be told that they should learn it
Okay.
very thoroughly and properly. Certain things are very difficult, students. It may not be easy. It may not be easy. Therefore, students, we can have different type of isomers which can be exhibited for the coordination compounds. Now, okay, we are proceeding further. Further, I am talking of students now. These were all structural isomers. What happened in structural isomers? What did you see in structural isomers? That the
Okay.
atom bonds, student, they are changing. They are changing. Here, the nitrogen was bonded. Here, you can see the what happened. CN is bonded, and in the second case, you see the atoms bonding has changed. And in the geometrical type of isomerism, there are certain conditions. It cannot be shown by all types of coordination compounds. Optical isomers. I will be mainly studying the geometrical and optical isomers. In the geometric isomers, student, the complex must be heteroleptic.
Okay.
Condition is geometric isomer will only be shown by heteroleptic complexes. The compound must be heteroleptic, and there are examples. Mostly we will be talking of coordination number 4 and 6. In coordination number 4, students, what could be the geometry for coordination number 4? What possible geometries are there in coordination number 4?
Uh,
Square planar,
octahedral.
square planar, or tetrahedral. Tetrahedral. In tetrahedral will not show, tetrahedral complexes do not show geometrical isomer. This question was given. They do not show geometrical isomerism. Which one? Tetrahedral. If a complex is tetrahedral students, then it will not show geometrical isomerism because the relative position of the unit and ligands attached to central metal atom are same with respect to each other. What is the shape of the tetrahedral? You have a metal student and you have the ligands. Supposing you have different type of ligands. One is L1 ligand, L2. Since it's tetrahedral, what will happen? Nothing. You can put these ligands anywhere. The relative position attached to central atom are same. Relative position, student, relative position. It is a symmetric figure. Relative position of the unidentate ligands are same. Therefore, it doesn't matter. And it will not show geometrical isomer. This question has been asked in the paper. Only left is scale planar for coordination number 4. And scale planar can show. Now, if I have students something, this is my metal
Okay.
and you have A4. A4 means all ligands same nothing because this has to be heteroleptic. Now, if I say A3 and someone B, what will happen? Now the question is only one ligand is different. You can put B anywhere. How does it matter? Nothing is going to happen. So if you have only single, no, not possible. For example, you have 3 same and you put B, or you can give a rotation to this 90-degree. What will happen? Nothing. So the relative positions are not changing. The relative positions makes no difference. You can put one anywhere. The relative positions will remain the same. And there will be no geometric isomers here. No,
Okay.
no geometrical isomers. Then where is the geometrical isomers coming? Okay. If I have M A2 B2, now the story will start. How can you put A and B relative to each other? Students, you have seen one we call as a cis. You have earlier also heard about it. Cis and trans isomerism. That means students, now if I have metal, this the shape is what? Scale planar. Tetrahedral cannot show. I am talking of scale planar, student. Is shown here, and in the three-dimensional picture, students, you can see these groups are pointing towards me, they are going away, and the easiest way for me is student when you put two groups across each other like this, what
Okay.
will happen? You will get one isomer, and next possibility, you can put two groups on same side anywhere, makes no difference. If I put AA here and B here, or I put AA here, B here, they are the same things. They are the same thing, students. They are equal, makes no difference. These are equal. So there will be two geometrical isomers.
Okay.
One is called the trans, other is called the cis. You can
Sis.
this. This is a question now which will be there. There will be two types
Okay.
of isomers. The two ligands can be arranged adjacent to each other. What is that? This is the cis isomer. The two ligands are adjacent to each other. You can put anywhere. And
Okay.
trans student, this is a transform. The two ligands are opposite to each other. Got it? Opposite to each other. This is how we can get the trans. Any one. Anything could be there. It could be MA2 or it could be BC. They are different, both of them doesn't matter. So the identical group on the same side, identical group on the opposite side. So you could write more than two also in certain cases, more than two also in certain cases. So students,
Okay.
if there can be three, then in such cases you will find, if you try, there will be three geometrical isomers. We have to put the groups different position and see how many are possible. That's all. So you can make an attempt. So you will get three isomers, two cis and one trans. Ma2, two cis and one trans.
Okay.
Trans will be that in which AA will be opposite.
Opposite.
You put
Yes, sir.
A opposite, one example is that, and you put A adjacent and change the B and C, you will get the three. Got
Yes,
it?
sir. Yes, sir.
Okay. For example, what I try to say, student, that you have metal, I put here B, A, A. They are opposite. You put A, B.
B, C. Yes, sir.
So this is trans. This is
Cis,
this. Now I have M,
M, A,
A, B, M, M, A, MA to BC, MA to BC. What I do, put A, and B, C. Then you put M, A, B, C. Other I put CB here, or makes no difference.
yes, sir.
So what we find, this is our cis variety. Now you can try more if possible, more if possible, we can write more if we can. In such cases, B and C are on the same side. If I put A, I can put C here, will be the same. If I change C to B, C to B, what will happen? It will still be the same because they are the same things. What else I can do? What else I can make, student? Here you have only this. If I have M, A, B, X, L, all the four are different. All the four are different.
Okay.
This is also two. Then why did I can't make more than two here.
Yes,
Only
sir.
two, only two. I have only two. One cis and one trans. But if I make A, B, X, L, now four different. Then you can try. Then there will be more than two. Then there will be more than two. Because we have to try, student. We can't just say without writing. So there are, after we start writing, there is some trick involved. If we know, we can apply that trick. Okay? Okay.
Yes, sir.
Then when four will be different, student, when four will be different, then four scale planar complex of this type, it is, there will be two cis and one trans. We can try and see that. These are usually not asked what I said. Most of the time, the type of questions we are giving to you. Now, There are two important points here. One, this you see this compound PTNH3 2Cl2. This is
Yes, sir.
important from medical point of view. See the difference, how much difference is there. In this compound, there is a cis form and there is a trans form.
Transform.
Cis and trans. I should put them in the bracket so that. Okay? The cis form is known as cisplatin anti-cancer drug. This is used as anti-cancer student. Cis, what is the name of this? Diamine dichlorido platinum. What is the oxidation state of platinum here? 2.
2.
This is also the same name, but this is cis, this is trans. That
Okay.
trans is highly toxic and this is used for anti-cancer drug. See the difference? This has a medicinal value, cis one. And trans one, if by mistake, if I give trans to someone, that is a poison.
Okay.
See, sometimes, chemistry is like that, students. The glucose which is going inside you, D-glucose. And what is the change in configuration, in D-glucose, the asymmetric carbon, the lowest asymmetric carbon which you have, lowest asymmetric carbon, the carbon 5, OH is on the right side.
Okay.
And if OH becomes on the left hand side, what happens? Then it becomes L, and the property and the biological function totally changed. In biology, this is in the biological function, this is very important. Their biological function changes immediately. The activity, you see, they are very specific reactions inside the body, very specific. So here, in the case of ethylene diamine, students, this is ethylene diamine, PT. These isomers we can easily write, no problem in this. You have two NH3 and two Cl2. You can easily write the cis and trans, cis and trans of this. This is important. If I write NH3 adjacent, this will be cis. If I write across each other, NH3 and
Trans.
H3 and Cl, that will be our trans isomer. And for if I say whether this will have geometrical isomers or not, PTEN twice. If I want to draw this, how will I draw it?
PT.
That is a bidentate ligand, student, for square planar. Can I write more than one possible structure for this compound? Can I write more than one possible
Yes, sir.
structure of this compound?
Mm, no, not more than one because it
Not
is a
more than
bidentate again.
not
No.
possible. Because this is the only possible position I can put. Only possible position is this. Opposite to each other.
Yes,
that,
sir.
that is a transform. That's all. There's nothing. Only one form is there.
Yes, sir.
Now it says draw the cis and trans isomers of the following compound, students. You are provided and you have to write the cis and transform. You have 1 minute. Cis and transforms of such complexity, students. You have iridium. One I will say NH3 adjacent to each other. And you can put Cl or Co. And in another case, what I do always. These are the ligands I put across. Adjacent and
Okay.
across, students. Now other one you put anywhere makes no
There's a
difference.
bit.
This is our CO. So I can put student, this is my CO. So you have trans and cis. Similarly, we can put these PH3 twice, HBr, platinum, AS3. All we have tried is to, sometimes you know what we do in the papers. We don't give the common ones which you are seeing in the books every time. You are doing a lot of cobalt, chrome. Do what the examiner does in the paper students. He will try to change this iridium or something. Even the ligands, are quite different. Students will feel, oh, what is the change? That is the reason we try to do variety of questions. Otherwise, there is no reason. If we understand, we can do it. But once we get ligands which are not common in the books, ligands or even metal ions which we are not using commonly in the book, then students may be having some difficulty. So
Yes,
students,
sir.
we have to understand and do some practice. It helps us. As I said, other square planar complex of the type students,
Yes, sir.
MAB sphere, AB, XLR unidependent ligands show three isomers, two cis and one trans. Okay, we can try to make them. Now, further in octahedral complexes, what will happen? Octahedral complexes, student. We have two types of complexes, square planar and octahedral complexes. See, in the case of the octahedral, there are six ligands. You have M and you have A4 and B2. When you have this type of situation, student, they will show octahedral isomers, they will show geometrical isomers. They will show geometrical isomerism. There will be cis and there will be trans. And one of the easiest way, I would say, would be what I will do, student. You know what is the shape of octahedral. This is octahedral. So these two are
Yes,
the
sir.
same. First, I will put it this way. And now put all others. Put all others. ठीक है? Got it?
Yes, sir.
These
Yes,
two
sir.
groups are on the same side. I call this as cis. You can try it. Second case, I will put them across. That's all. I will not do anything. I will not do anything. What I will do, student, I will put B and B across. See, and put all other groups. This is the easiest way, student, to make cis and trans. The more we try, we can do it. These are three-dimensional picture has been shown, which is difficult to draw on the board, student, that we have to take from some source. Because I can't draw this three-dimensional, it is difficult. Only the dashed lines, or they are going away from us, they are pointed towards ourselves. You know, the properties of cis and trans will be different. The properties of cis
Yes, sir.
and trans. Which main property will be different? That is the question. Which main property will be different now is important. What property you are expecting to be different? Tell me, do you can see one important property which will be different in cis and trans, which we can make ourselves now? What comes in our mind first? And that could be a question on that. That's what I'm saying. You know dipole moment?
Yes, sir.
Dipole moment will be different
Yes,
na,
sir.
because cis and
Yes, sir.
trans, they will have different dipole moment. And if dipole moment is different, their melting points will change. Important. Melting points, because if there is a more charge separation, students, the melting point will increase. If there is a less, the melting point will drop. So
Yes, sir.
we can expect this type of question in this.
Okay.
We have to think without thinking. I mean, if questions are framed like this, they make small changes to the students. So I hope you have understood these geometrical isomers. So we
Yes,
will
sir.
go further in our next class. and try to solve lot of questions which are been asked in the papers. Okay, then good night. I will meet you in the next class.
Okay.
All right, keep practicing and keep
Okay. Thank you, sir.
okay.
Yes, sir. Okay. Thank you, sir.
Okay, good night.